Okay, we're about to finish dotting some I's and crossing some T's in Chapter 7, Hypothesis Testing, to compare two population means with two sample means. Implicitly, we're tackling the issue of whether the null is true, with the null being almost always no relationship between the explanatory and response variable. In this case, explanatory variable corresponds to which group are you in. And so the no relationship condition would correspond to having the same population mean in each of the two groups that we're dealing with. Okay, so with all that as preference, or sort of like the starting place, let's see if I can find my mouse. Okay, there we go. Boom, moving forward a little bit. So sometimes your natural question will come in a directional format. For example, not is there a difference between the two means, but rather is the one mean higher than the other? In a study in Santa Barbara, California, they had a group of breast cancer individuals who had been diagnosed with stage 4 breast cancer, and they were put into two groups by random flip of a coin. One group was given the regular treatment by their oncologist, and they were, whether it was a mastectomy or whether it was chemotherapy or both, and then radiation was mixed in as well. So there's a lot of possible ways of being treated, and those patients were all being treated by their oncologist, the cancer doctor, according to what was best. And by a flip of a coin, some of them were put into a treatment group where they were encouraged to come to the hospital Thursday mornings at 7 a.m. to do some group therapy, chatting with others who were also undergoing breast cancer at the same time. And they were working with a therapist who helped them sort of process their thoughts and feelings about having the illness and the treatment and the difficulties in the treatment and all that sort of good stuff. The other group, they were not forbidden from coming Thursday at 7 a.m., but they were not sent a special letter encouraging them to show up. So the treatment was really getting the letter. Everyone had access to the information in their pamphlet when they sort of checked out of the hospital from their surgery or their radiation therapy. They were all informed, but the one group was given a special letter saying, please come. We find that people who go through this process with group therapy are often healthier in the long run. So I want to know, does group therapy increase the survival time of these breast cancer patients? Okay, so it seems like the alternative and null hypothesis are going to be, I would say, not straightforward, but they're easy to work with. So let's look at the data. I've got the data here. Survival in months. Now, these are stage 4 breast cancer patients, so the survival times were often quite short, and they're in the control group, or later down, there's the treatment group. Under analyze fit y by x, again, I'm doing it for you to show you what the output looks like because it's going to be on your test. The treatment control versus group therapy will possibly impact the length of the average survival time. I click OK. We see the graph opening up, and the graph here suggests that the group therapy group seems to have a larger average than the control group. If I were to turn on the means and standard deviations, you've got all the sort of good information that would allow you to calculate a test statistic T, literally the sample size for each group therapy, the average and the standard deviation, or better yet, the standard error. Similarly, for the control group, the sample size, mean, standard deviation, or standard error would be nice. If you were to turn on your test statistic T, your T-test, we can see down here at the bottom, okay, the two-tailed p-value, 0.0081, 0.0081. I want to know, as my null hypothesis, okay, so null hypothesis, The null hypothesis is that mu of the group therapy group equals mu for the control group. My alternative hypothesis is that mu for the group therapy group is going to be, instead of equals to mu for the control group, it's going to be larger than mu for the control group. Okay. So for whatever reason, our software has chosen to go with control minus group therapy is its way of describing things. I guess I could scratch out my null and my alternative hypotheses to correspond to the way that they've written it. Okay, yeah, literally, they have the group therapy group second, control group first, second and first maybe makes a difference. So I could say that mu for the control group is less than mu for the group therapy group. Same idea, but notice that the control group is listed first and group therapy second, just like in the output. And if the alternative is true, control minus group therapy will tend to be negative, like we see in our data. Negative 2.78 is our test statistic. 41 degrees of freedom. Let's look and see if we could find with 40 degrees of freedom that error rate, that p-value, if you will. Okay, so I'm going to do a drag and drop. 40 degrees of freedom is down here towards the bottom, and I'm going to try and circle the 40 degrees of freedom row. So 40 degrees of freedom, there we go. And my t value of 2.785, 2.785 would appear here. If it were in the t-table, that's where it would be. If I read to the top, I'm going to find that my upper tail area is between 0.001 and 0.005. 0.001 and 0.005 are the limits on my upper tail area. Now, for our situation, the survival times being larger in the group therapy group, okay, more extreme, corresponds to only values that are, if you will, way the heck down there and even further, okay? So my p-value is only the lower tail, which we have found due to symmetry is less than 0.01 and greater than 0.005. My p-value is somewhere in the range 0.005 to 0.01. Okay, so with a p-value of somewhere in the range 0.005 to 0.00 and 0.005 to 0.01, you would conclude the alternative hypothesis ought to be believed. Alternative hypothesis ought to be believed. Okay, 0.005 to 0.001. I'm sorry, I got that wrong. 0.001 to 0.005. There we go. 0.001 to 0.005. 0.01 to 0.005. Certainly smaller than that nominal 0.05 value, which would cause us to believe the alternative hypothesis. Let's maybe slide that back to the other side where we can see our slide. Okay, so easy to do. Really, if you have a one-tailed test, it's more powerful. Did y'all spot that the two-tailed p-value, in our case from the software, it's 0.008. For the one-tailed test, it's cut in half, 0.004. The p-value being lower means we're more likely to spot the alternative as true if the alternative is, in fact, true. Okay. More powerful. We're more likely to spot the truth. So here's the quick summary. Same deal as before. The null hypothesis has an equality in it. The alternative hypothesis will either be mu1 is greater than mu2 or mu1 is less than mu2. If you're doing it by hand, I recommend putting mu1 as corresponding to the first group, the larger mean. If the software dictates for you which group is called group 1, its group 1 is the one that's first. The second one is the other of the two groups. The test statistic is the difference of the sample means, just like before. Degrees of freedom, just like before. The standard error, just like before. The p-value is only slightly different. The p-value is half of the former p-value. Your conclusion will, of course, be the same. If the p-value is less than alpha, you reject the null hypothesis. Otherwise, you continue to believe the null hypothesis. So let's look at graphically how that would work. If the null is mu1 and mu2 are the same, and the alternative is that mu1 exceeds mu2, you're going to find an upper tail area only for your p-value. If mu1 is less than mu2 as your alternative, it's only a lower tail area. And you don't double a tail area to get a p-value. The p-value is just what's found in one tail or the other. Okay. So let's try an example with breast cancer survival. Oh, we already did that. Let's try with a different example. We're going to go with ice creams, and then a third example with the great blackout. With the ice cream data set, again, like before, fit y by x, we're going to say calories, okay, and flavor category. And I want to know if chocolate has more calories than vanilla on average. Again, chocolate more than vanilla on average. Here are the dots in my dot plots. Turning on the t-test, we see vanilla minus chocolate. It's chosen for me vanilla, and chocolate is the group to which we're comparing. And if chocolate had more calories than do vanilla, we would expect a negative value for T. We do get a negative value for T, and our probability less than that lower tail area is 0.2551. My p-value 0.2551 basically says what's the chance that we could have a gap of 9 calories per half cup serving, 9.150 calories per half cup serving, if indeed chocolate and vanilla are the same. Okay, what's the chance that chocolate has more than 9 calories than vanilla on average? 0.25, greater than that 0.05 cutoff. I'm going to believe the alternative. No, I'm going to still believe the null hypothesis. I'm not yet convinced that it is wrong. One last example, it's the births, okay? And maybe if I knew something about OBGYN, like a good friend of mine, David, does, he's an OBGYN, he would be the first one to say, oh yeah, of course you have more births per day on weekdays than weekends. And he says that's true even if you factor out scheduled births through whether it's an induction or a cesarean section, both of which can be started out. It turns out that his colleagues that he says he has respect for, but sometimes they cut corners and they say, you know, if it's a birth that's coming in on a Friday morning, let's just give a little hormone to rush things so that way we can get out the door by Friday afternoon late and we don't miss the golf game on Saturday. I mean, that's very cynical on my part as someone who's looking at another profession, doctrine. And, but doctors that I know uniformly, regularly say this is what happens. So my null hypothesis might be an equal number of births between weekdays and weekends, but perhaps there are more births on weekdays than weekends would be my natural alternative hypothesis. Again, under analyze, fit y by x, let's compare the number of births per day on average across the two different types of days. I click OK. I see the data suggests that weekdays may be more than weekends on average in my data set. My t-test basically says weekends minus weekdays. That's going to correspond to a negative value if my alternative is true. If really weekdays have more bursts per day than weekend days do, then mu for weekend minus mu for weekday will tend to be negative. My t ratio being negative and my p value being 0.0002 says in 2 out of every 10,000 such studies would I see a difference this big, a difference of 77 bursts, if in fact the null was true. In 2 out of every, again, 10,000 studies would I see the extra number of bursts on weekdays over weekends being about 75 or so, if in fact the populations were even in terms of their average. Okay, so not too bad, easy to do. It's just a matter of plug and chug with our numbers, okay? So here's the way we're going to round out the rest of chapter 7. Conceptually, I like to perform a hypothesis test first. Most people who are statisticians or researchers naturally find it easy to tackle the question, is there a difference between the means? And then if they do find that there is a difference between the means, they'll use a confidence interval to find out how much different the means are from each other with a margin of error. Okay? If, excuse me, if the sample means really aren't that far apart, then we can't even conclude that the means are different. And where is my mouse? Oh, it was doing bad stuff earlier. If we can't even conclude that the means are different from each other, why bother even doing the confidence interval? Again, null hypothesis. It's only if you reject it would you want to go with the confidence interval. Which raises the question of statistical significance. Literally, is there a difference between the two groups? Statistically, is it noticeable? And practical significance. How big is the difference between the two groups? Okay, if we have statistical significance and if we have practical significance, I'd say those results are real and important. Okay. Again, rejecting the null says, aha, we believe there's a real difference between the two groups. Practical significance says these two means are different enough from each other that I'm convinced that not only is it real, but it's important to me. The margin of error in a confidence interval is either small or large. If the margin of error is small, we would say we are precisely able to know the difference of the population means. If the margin of error is large, we're not so sure what that difference of population means is. Okay, so with all that in mind, let's finish it up with considering the 4 possibilities. What if you have statistical significance and practical significance? There's a real difference, statistically significant, and you care. If there's statistical significance, but no practical significance, there's a real difference, but you don't give a rip. An example that might be if you had a study of 2,000 males and 2,000 females all in the college age group and asked them, what is your blood pressure? Systolic blood pressure is the first number that they get when they're reading your blood pressure. If the male systolic blood pressure is 2 points higher than the female systolic blood pressure on average, and it's noticeable, that difference, it's statistically significant, a real difference. But 2-point difference between the male and the female, no one thinks that would matter. If you go to your doctor and says, my blood pressure went up by 2 points, your doctor is going to say, so why should we care? Yeah, a 2-point difference is not a big deal. What about no statistical significance and a small margin of error? There might be no difference at all, but even if there was difference, it's a difference you don't care about. I mean, seriously, no statistical significance means we can't even spot a difference. And the margin of error being smaller really means the margin of error being small really means that we're pretty precise in our knowledge about the difference of the population means. And if that is small, there's not a noticeable difference. But if there was a real difference, it wouldn't be very far from zero. The fourth case is no statistical significance, but a wide margin of error. Think this. I can't tell you that the two populations even have a different mean. But if the margin of error is plus or minus huge, any of the values inside the margin of error are possible or plausible for a difference of the two population means. Wouldn't you want to tighten that in? Tighten down the margin of error, if you will. Not only might it make the results statistically significant, it's certainly going to be allowing you to say more precisely what the difference of the population means is. Okay? Usually more data is the best solution here because more data will allow you to see if there is a statistically significant difference. If there really is a difference, more data will spot it, and more data would also tighten down that margin of error. So to get after a couple more things, conditions for the t-test. If we're comparing two means, just like with the two sample confidence interval, you need to have a fair sample from each of the two populations that's independent of each other, or you need a fair sample from the one larger population that you subdivide, post-stratify, if you will, into the two different groups. If you sample from people, you classify them as male or female. If you were choosing to sample separately among males and then among females, that would be absolutely fine. For each sample, you need either the sample to be large or the population to be normal. Usually, like we mentioned before, two large sample sizes would be typically the way you go, or you have to assume that the two populations are normal if the sample sizes are both small. Very rarely will you have one large sample and then the other population being normal. And we've checked these with ice cream before, so we don't need to worry about that. Seems to be a good place to stop. The other thing you might want to do to prepare for your exam is to look over the sample exam questions. In the next day, I should be getting a collection of answers online to those sample exam questions. Again, the answer's already there, but students sometimes like the verbal explanation, so I'll be recording some quick videos of the answers to each of those 4 sample exam questions. But that's for the future. Enjoy the rest of your day. We'll see you in the future. Bye-bye.